Okay, here is a review for our homework 4. So this first one, we definitely would prefer the 10 grams of liquid water. Why? Because if I take 10 grams of vapor water and I apply it to the skin, then I'm going to take all of the energy from the 540 calories per gram, which is the amount of energy it takes to get liquid water per gram into vapor water. So that's going to be 10 grams. So that's 5,400 calories of energy. And that's going to go into my arm. Okay. And now that I've absorbed 5,400 calories of heat, now I've got 100-degree liquid water on me. So I either start with 100-degree liquid water on me, or I put 5,400 calories into the skin and then put 100-degree liquid water on me. So definitely do not want the vapor, because then I have to deal with the heat of vaporization. Oop, that's too much. All right, so we're going to do this. Calculate the enthalpy problem. Let's see, what do we got here? Well, the methane is on the wrong side. So I'm going to write CH4 arrow here and then get rid of this and change the sign to a positive. And let's see, the bottom one is twice as big as it needs to be. So I'm going to divide you by 2, and that'll turn you into a 1, make you a half, make you a 1, and make you a half. And then we divide this by 2. And then the ammonia, we got to flip that around. So NH3 goes this direction, 2 of them. And then I'm going to cross this whole thing off. And then I'm going to change the sign on that. And let's see, we've got, let me change my color here. Black is not going to work on this background. So this green, that'll work. Alrighty, so let's see. I've got 1 methane gas and 1 methane gas as a reactant. Oh, I messed up. I didn't, I got to divide this by 2 and this by 2, so that's a half, and this by 2, so that's 3.5. And I got to divide that by 2. Okay. So now that this has been divided out, then there's only 1 ammonia. All right, so then there's my 1 ammonia on the reactant side. I've got 1 cyanic acid, 1 cyanic acid on the product side. And do I have 3? Do I have 3? It looks like more than 3, doesn't it? Let's see. I got a half of nitrogen that's going to get canceled out with this half of nitrogen, because this is on the reactant side and that's on the product side. And let's see, I've got on the product side, I've got 1 carbon here, and on the reactant side, I've got 1 carbon there. So I need to get this up to 3. Seems to be more than 3, right? There's 2. There's 1.5. And here's a half. So that would be, let's see. So this is on the reactant side. This is on the product side. This is on the product side. Oh, okay. So reactant side, a half a hydrogen, and I have a half a hydrogen here. If I take that off, I'm left with just 2/2, so 1. And so that will get me to my 3 hydrogens. Okay. All right. 3 hydrogens as products. All right. That worked out. Okay. So what do we got here? There is my calculator. So that's 91.8 divided by 2 plus 74.9 plus 270.3 divided by 2. So I get total, this equals 255.95 kilojoules per mole. And let's see, what do we got here? three significant figures. So my answer is 256 kilojoules per mole. All right. What's wrong with the phrase polar ionic? Yep, that's a problem. So ionic means a transfer of electrons. And polar means uneven sharing. There is no sharing in a transfer. So a polar bond has to happen with a covalent. Covalent is can't spell covalent. Covalent is the only option for a polar bond because there's sharing. And so polar just means uneven sharing. So it's got to be a polar covalent bond. What types of, okay, so covalent can, and ionic cannot. That's easy. And that's it. Okay, so that was homework 4. Okay, and here is homework 5. So we're going to draw the Lewis structure for these guys. And so I've got 3 valence electrons here plus 7 times 3. And so that equals 24 electrons for my aluminum chloride. We need to remember that aluminum violates the octet rule. And so aluminum only wants to see 6 total electrons. So we're going to have to think about that, putting this together. I'm going to put the odd element in the middle, and then I'll put the chlorines around the outside. So those lines mean we've used 6 of our electrons, and we need to use 24. And the aluminum's happy because we said that it only wants to see 6. And then if I put 3 lone pairs of electrons around each of the chlorines, then that gets me to, there's 8 here, 8 here, and 8 here, and that gets me to 24. So this structure, there is no VSEPR structure. The reason there's no VSEPR structure is because there are no lone pairs of electrons on the central atom, right? And then the molecular, that's going to be trigonal planar because it's a central atom with 3 things around it. So it would form a triangle. All right, so this one's a little tricky because there are 2 central structures. So I've got 4 plus 3 plus 6 plus 1. So we've got 14 electrons here to deal with. I'm going to put a carbon here. And I gave you the condensed structural formula, so that would help you figure out how to connect these guys up. All right, so I have used 2, 4, 6, 8 of my 14 electrons. Maybe it's not 14. Maybe I can add 4. No, let's say 14, right? 2, 4, 6, 8, 10. Oh, that's how I can't add. I've got 10 already. And so now I just have 4 electrons I have to deal with. Everybody's happy with the exception of this oxygen. Okay, so we're good to go with that. All right, so now we're going to talk about the VSEPR structure. So there is, for the carbon, valence shell electron pair repulsion is an Na because there are no lone pairs of electrons around the carbon. But for the oxygen, my VSEPR structure is tetrahedral. The reason it's a tetrahedral is the oxygen sees 1, 2, 3, 4 things. And so 4 things means tetrahedral shape. All right, so molecular. My carbon sees 4 things around it, so we just said that's a tetrahedral. And then for the molecular, for the oxygen, anytime an oxygen is connected to 2 different things, it's going to end up being this bed shape. So we end up having this carbon, the CH3 carbon, going to an oxygen, going down to a hydrogen, and those lone pairs of electrons are up here. And so there's my tetrahedral shape. And then if I'm talking about the molecular shape, I just ignore the electrons and say, now what do I have? And my shape is bent. All right, so calculate the formal charges for the atoms here. Okay, so carbon and the hydrogen and then the oxygen. All right, so for my carbon, I've got 4 valence electrons, and my hydrogen has 1 valence electron, and my oxygen has 6 valence electrons. So I'm going to subtract off lone pairs, and so that's a 0 on the carbon, a 0 on the hydrogen, and a 4 on the oxygen. Then I'm going to subtract off 1/2 the bonding electrons, and so the carbon has 8 bonding electrons because it's connected to 4 different things, and that gives me a 0. So 4 minus 0 minus 4 is 0. And then my hydrogen has 1/2 of 2, since it's got 1 bond. And so that also is a 0. And then for my oxygen, it's 1/2 of 4. And it's 1/2 of 4 because it's got 2 bonds. So that's 4 total valence electrons. So that's going to give me a 0 as well. So this is the correct structure that we've got for my methanol molecule. All the formal charges are 0, and that's what we're hoping for when we do formal charges. Requirements for a sigma bond. Sigma bond must have s electrons. Electrons that are from an s orbital. And for a pi bond, they must be from a p electron. So my s orbitals are those spheres, and my p orbitals are the dumbbells. So if it comes from an s, even if it's combined with p's, it still comes from an s, and so that means it's a sigma bond. And if it's a pi bond, that means it's just p electrons. Draw the Lewis structure for methane, ethane, and dihydrogen sulfide. All right, so methane is CH4, and ethene is C2H4, and dihydrogen sulfide is H2S. All right, so I've got 4 plus 4, so there's 8 total electrons here. I've got 4 times 2 plus 4, so that's 12 total electrons. And here I've got 2 plus 6 gives me 8 total electrons. All right, so carbon, hydrogen, 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 and I'm done with the methane. That's it. With my ethane, I've got a carbon, and I'm going to connect the other carbon to it, and a hydrogen, and a hydrogen, and a hydrogen, and a hydrogen. Remember, nature likes symmetry. And so now I've run out of atoms. The hydrogens are obviously happy. The carbons see 6 electrons. They need to see 8. I've used 10 of my electrons. So I can either put a lone pair here, which satisfies this carbon but not the other, or I can put a lone pair here, which satisfies this carbon but not the other one. Or if I get in that situation, I put a double bond. And there we go. I have a double bond. And then my last one here, I'll put sulfur in the middle, a hydrogen on each side. The hydrogens are happy. I've used 4 of my 8 electrons. I'll put 2 electrons here and 2 electrons here. And this looks just like a water molecule's Lewis structure because sulfur and oxygen are in the same column. So they're in the same family and have the same chemical reactivity. Explain hybridization of electrons in carbon using energy level diagrams in your explanation. All right, so I've got 1s, 2s, 2p. So my carbon atom has 6 valence electrons, and so 6 electrons. So those are those electrons. And so what Linus Pauling had said was that the distance between the 2s and the 2p is much closer than we give it credit for, and we end up having 1s, 2sp3. One here, 1, 2, 3, 4. So the 1s looks the same. So the reason that there are 4 orbitals here now is we've taken this orbital and brought it up a little bit, and these 3 orbitals and brought them down a little bit, and now they're all at the same energy. And so now that they're all at the same energy, I disperse one electron into each one of the orbitals per Hund's rule, and that allows the oxygen or the carbon to make 4 bonds in 4 different directions. Explain what's happening with the bonding of the ethene molecule. Okay, so this carbon is forming a sigma bond this direction, and that direction. This carbon is forming a sigma bond there, there, and there. And then over the top and the bottom, there's one electron here, one electron here. It can go, this electron can be up top or on the bottom. This electron can be up top or on the bottom. And they overlap their orbitals. So now this one electron from this carbon can be anywhere in this space. And this one electron from the other carbon can be anywhere in this space. And that allows this molecule to be doubly bonded. And so the double bond kind of, I don't want you to get the impression of like 2 ropes. Instead of having 2 ropes, I've got like a rope between these things. And then I've got 2 more ropes above and below, or maybe pieces of wood would be better, connecting above and the bottom, sort of like a frame. And so I've got these atoms, the hydrogens and the carbons are all flat in a planar structure, because this is trigonal planar because it's sp2, and this is trigonal planar because it's sp2. And then the last electron for each carbon is above and below the bond, which makes those electrons very chemically reactive, because instead of them being sandwiched in the middle like these guys are in between these 2 atoms, they're above and below and very accessible for other molecules to come in, other atoms to come in and react with them. So this ethene molecule is a million times more reactive than the ethane molecule, which just has all single bonds. That's it. Okay.